sensing. So second, okay, this is a single force based sensing applications. So these are the how the applications are. I have just summarized here. In terms of, it is like a single photon sensor design and an application in various fields. So this is the AI generated images. Just I want to give you the overview of what I'm going to discuss. And before we go discuss these applications, so we have to know why single photon sensing is required. Okay, that part also I will discuss, and also what is single photon and what you're going to gain by the doing the single photon sensing. So these are the applications at variety places in space, in medical, or in a variety of places. It has a sensing applications. I will discuss in 4 to 5 applications, and you will know what I'm talking about. All right, so this is how the lecture is being organized. And first I will discuss why single photon and why not multi-photon. Okay, why single photons plays a crucial role compared to the existing technology. Why single photon is so important. And what is a single photon sensor and how to design the single photon sensor. And what are the quantum features are enabled if you use a single photon sensor in a sensing technology, and what are the existed platforms in the world which are developed for the sensing purpose. And these are the 5 applications which I am going to discuss. So from the imaging to the at the end to the fiber networks, how in the LiDAR and metrology and sensing, biomedical sensing and all, how this single photon sensor play a crucial role. Sorry. Then after that, so I am going to discuss what are the emerging research directions in this at the state of art, and how to push in future, and what are the challenges exist. So making a single photon sensor, it's not that easy. Just remember that you are making only one photon sensor, which is a very okay. And why single photons? Why not classical beam? You have already learned, right? So the when you present sensing technology is fails when it goes to the nanoscales, when it goes to the low photon number. Low photon number means usually in the present technology used many photons in the order of 10 raised to the power 4 or 3 or maybe 5, because these are in this if you go to the low photon number in the classical regime, what will happen is that there is always something called short noise. The noise which is generated from the equipments or noise which is generated from the signals, it is predominant than the signal. Okay, and if you are trying to measure in the present technology with the small signals, very small signals which is scattered from the very small objects, so it is usually it is buried under the background. Let us say that in your experiment you have 100 background and you have a signal of 1. You will not be able to see that one above 100. You have to do it in opposite way, saying that your signal also 1 and also your background should be much less than 1, then you will be able to see. Okay, so this short noise, what we are talking, this dominance, this arises the discrete nature of the photons, which is we already learned. So it is unavoidable in classical. It's always there. Okay, so then if you use a classical coherent light, which is a laser light, then that is always there. Then there is something called a standard quantum limit for classical light. It is which is a proportional to 1 over square root of n. Okay, so the where n is being the number of photons. Okay, so if the number of photons vary, then your limit will vary. Okay, these are the issues in the classical thing. So you need a ultra low power light detection. So which means that your detector should be sufficient enough to detect one photon. Okay, that is the one thing. We should able to generate that one photon, and you should able to use that one photon for the applications. This is very important. All right. So this since it is only one photon, it is a very ultra low light. The high sensitivity can be change the quantity being is sensed. Since it is one photon, it is very sensitive whatever the quantity you put vicinity of it. Okay, so especially in the biological samples. So you will be able to even image or detect the single biological molecules or single proteins or single cancer cells. Such sensitive you can reach if you are using for your experiment single photon. And it causes optical heating in nanomechanical systems. So which means that the nanomechanical systems are very small, right? So it can cause very small heating, optical heating. Okay, and that therefore that also it can be as a sensor. Okay, that's very important. So since ultra low light detection, since you are see in the present world, suppose in the medical field, if you want to detect anything, you send a bunch of light, right? So then it is you are detecting and also parallelly you are destroying also. Please remember. Okay, it's also destructive technique. Some of the good ones you are also destroying. You may destroy if you send really high light pulse. Okay, but if you send only one photon, is what is going to happen is that you don't destroy that. Okay, and it's like you don't perturb much system. So it is like a very light, and you can sense it without any perturbation to the system. Okay, so this is the advantage quantum side which you use a single photons, which you are going to gain is a single photon sensitivity. It's very high, and it is a non-classical correlation because it's a single photon. It exhibits the non-classical correlation, and it acts as a noise suppressor because it is a single photon. Okay, you are going to have a very low noise. This is the why we need to use a single photons. So which means that the conclusion, the message, take home message from this slide is that single photons enable sensing at the ultimate quantum limit. Okay, the single photons, it's the ultimate quantum limit. There is no better than this limit. Therefore, we do the experiment at single photon level so that you can get a ultimate sensing. This is the most important point. Then how to design a single photon sensor? So in order to design a single photon sensor, single photon is a measurement it's a measurement approach in which physical information is encoded and also retrieved from that using individual photons. It's like a individual photons means one photon. Each time you encode some information, and after some time you decode the information from that photon. Can you hear me? Hello? Is there anybody? Can you please somebody message if you are hearing?
There is some problem. in last 1 minute. Can you please repeat?
Okay. Can you see the slide now?
Yes, we can see the slides.
Okay, thank you so much. Okay, the single photon sensor, essentially it means that you have a, in the sensing, in the measurement approach, the information is encoded and retrieved using the single photon, only one photon of the field. Okay, this will typically happen for developing of single photon. It's involved first you have to generate a single photon first, and it has to be interacted with the target molecule through the target. Suppose if you want to sense the biological sample or chemical sample or anything, and it has to propagate through that channel, and you have to detect with the single photon detector. Then you have to analyze the photon counts coming out of the sample, then estimate the whatever the required parameters. This is how it looks like. So you have a single photon source, you generate it using a different technologies. So single photon can be generated using a single quantum emitter, or you can generate a SPDC, spontaneous down conversion. And also you should have a sensing channel. That means the single photons can flow through some channel, which is a typically people uses, and or in our lab we are using the optical fiber as a quantum channel, and at the end you should be able to detect the signal. Okay, these detectors are usually used APDs or the SN SPDs. APD means avalanche photodiodes, and SN-SPD means superconducting nanowire based photodiode. Okay, which I am going to discuss these detectors in the further slides. So these detectors' specialty is that it can detect one photon at a time, so that you can measure all the single photons which are coming from the quantum channel, so that you can sense in the path whatever you have. Okay, so what are the features it enables for high sensitivity? This is very, very important. The first clear feature is that photon anti-bunching. The photon anti-bunching is when you have a zero delay, at zero delay, so close to zero correlation or less than 0.5 correlation, it is called photon anti-bunching. These coincidences are measured for the single photon, then it exhibits the photon anti-bunching. It's the true quantum nature of the photon which is being emitted by the single photon emitter. Okay, it is being experimentally observed in this paper in down 25 years ago. These correlations are called quantum correlations. These correlations are called quantum correlation. So the first feature is that you have a photon anti-bunching, and you have a second feature is that you will see true quantum nature of the photons, and interferometric phase sensitivity it will have. Since it is if you construct the interferometer with the single photon, so you are going to see it's very sensitive, the sensitive, phase sensitive. If you can measure the phase by measuring the shifting the by observing the shift in the fringes, then you can attribute that one to the position, which I am going to discuss in the application. And most importantly, the photon counting statistics. So how many photons are coming each time? So that will tell us that whether you have a subposition statistics or superposition statistics. These four features, it's everything is in a quantum that enables your sensing much higher. This is a very, very important point for the single photon sensor. So these are the platforms, okay, in the single photon generation, how in the history it has been done. Okay, so the single photon generation, it's a probability. There are two ways. One is how probable it is, and another one is how deterministic is. Okay, which means that suppose you give a photon to the one atom or some crystal, what is the probability that you are going to get one photon, single photon? Okay, conventionally from the history, people uses some non-linear crystal. When you pump, you are going to generate two single photons, which is one is called signal, another one is called ideal. This process is called spontaneous parametric down conversion, SPDC. This is how the people conventionally done. But this process is mostly it is a probabilistic. So the probability of generating a single photon in signal and idler is very small, in the order of 10 raised to the power -3 to -5. Such low efficiency. So then how to generate deterministically? So in the 2000, early of 2000 and 2000, the Jeff Kimball from the Caltech, what he has done is that he trapped one atom in the cavity. If you trap one atom in the cavity, if you send a probe laser, if you send one photon, you are going to get one photon out. Okay, it is highly deterministic. You give one photon to the system, you are getting one photon out of the system, 100% efficiency. Whereas here the efficiency is very poor. That is very important. And not only these natural limiters, there are artificial limiters people are exploring and investigated already in the last more than 25 years. Very recent one is this one. It's a defects in the nanodiamond. So the defects, you can have a nitrogen vacancy centers or you can have a silicon vacancy centers. So especially here, what I show is it's a nitrogen vacancy center. It's unfortunately people found that the defects in the nanodiamond or the diamond, if you use as a single photon source, the efficiency is very poor because of this crystal structure, and it is leaking to the other channels, non-radiative decay. Okay, but there is a way that you can get a single photons out of the vacancy centers in nanodiamond. Then there is another way of getting the single photons, which is a quantum dots. When you have a bulk, okay, when you have a bulk, the band gap is very small. Then when it is becoming smaller and smaller nanoparticle, you see that your band gap is increases when you excite the quantum dot, and it goes to the higher state and it decays to the lower state. When it decays to the lower state, you are expected to see one photon out of the system. These observations have made in recently and also in the past it has been made. These all platforms are the single photon generation platform. Okay. So for the sensing, as I said, you need to do three things. One is single photon generation. Second is single photon detection. Third is single photon manipulation. That's where the sensing part will come. Okay. If you can manipulate the single photon, that means that you are sensing. This is a very important. So then these are the generation protocol. Okay. Then these are the single photon detection protocols. Conventionally, most of the people uses that because it's a cheaper. It's an avalanche photodiode. This is how it looks like. It is sometimes it is called SPAD. So single photon avalanche photodiode, or the SPCM, single photon counting modules. You can see here it is written photon counting module. So this is a single photon counter. How does it looks like? We have about 3 in our lab, these counters, so that we can use it detect the single photons, which I'm going to show you at the end. Okay. So it generates the electrical pulse. You are counting the electrical pulse. So that consequently give you the how many photons have arrived to the detector. And another thing is the transient edge sensor, which is developed. You can see the scale is in the order of 10 micrometer. Then this is how the optical image of edge sensors it is being as a detectors it has been used. And the most important and most state of art, the best detector is the superconducting nanowire single photon detectors. These are the metal nanowires. So it has formed like a patterns like this. So it is works at very high, low temperatures like a 2K. And when the photon comes, it creates a Cooper pair. So then it's because it's a superconductor, right? It's superconducting based. So it's a nanowires are there all the way. When photon comes and heat, then it generates a Cooper pair. Then the Cooper pair, due to the Cooper pair, you will see some small current is flowing through the circuit. Okay, this is how the detectors have been established. So in our lab we have this, and these are the other two are very expensive. Especially this is the best detector in the world one can get. So this is very expensive. So therefore we could not afford. So now, as I said, you can generate a single photon and you can detect a single photon. Two jobs are done. The third job is you need to manipulate the single photon. So if you want to manipulate the single photon, you need to integrate with some structures. You need to integrate with some schemes so that you are able to manipulate the single photon within that structures. Okay, this is what it's called a system integration. So people in the past, they have used the solid immersion lens. They have taken the solid immersion lens and manipulate the single photons or the collect the single photons from the single quantum emitters. And this work is from the again Stanford Yoshi Yamamoto's group. So he has used a micro cavity, and there is a single quantum dot inside sitting the cavity. If the dot emits the photon, the single photons are propagated on top. And this is a work from the Stanford where they make the photonic crystal. When you have a single quantum emitter inside, then you can get the emission out of photonic crystal. And this work is a plasmonic metal nanowire. So plasmonic metal nanowire, if you have a single quantum dot sitting or single quantum emitter sitting on the nanowire, you are expected to see the single surface plasmon, which is a quantum plasmonics. This has been done by the Harvard University in the group Professor Mesha Lukin. These in the world, it has been widely done from the last, I will say, last more than 15 years. Okay, so then these are all our different platforms. Most easiest or the most adaptable platform is a fiber integrated platform, because in our daily life you see the most of the places for the communication, for the internet, for the medical, for many things you use a fibers. Okay, so therefore that means that if you are able to manipulate or if you are able to sense with the fibers, standard fibers, it is really useful for the human life, right? So therefore, when I started working during my PhD, I started working with taking a fiber and making a nano structures, and you try to manipulate the single photons using those structures. So this also not only the fiber, like the people have done cavity structures, we have incorporated the cavity structures on the nanofiber so that you can manipulate more efficiently the single photons. So recently, that not only the cavity structures, then also gold nanorods, because it's a plasmonic metal structures like this. So you can have a gold nanorods on the fiber along with the quantum dot, so that you can manipulate the single photons more efficiently. In our lab, we have a in our University of Hyderabad lab, we have a nano tips which can manipulate the single photons, which we are using in our present applications, which I'm going to discuss at the end of the this thing. So this tip makes very convenient because it is approachability everywhere. It is easily can approach any location on the sample or any location for that matter in the place. Okay, so now you learn how to generate a single photon. Now you learn how to detect a single photon, and you learn how to integrate a single photon. Okay, so how to manipulate a single photon. So single photon generation, detection, manipulation you learn. Then the fourth part is application. So now you can generate a single photon and you can detect a single photon. Then you can manipulate a single photon from one place to another place. Now, what are the applications this will give you? The first application it will come is a quantum imaging. Okay, so you can do imaging of any any object with very high precision. Okay, the principle is very simple. It exploits the quantum properties of the light, such as a single photon, and also sometimes people use entangled photon, or some people use a squeeze and photon correlation to perform the images. So I will show you typical experiments people who have done. They say it's a ghost imaging, but actually please remember that the object is never directly imaged by the camera. So the image reconstruction was done by correlating the photons, because the one photon you can't see in the CCD camera. Okay, so you have to reconstruct the image by taking the correlation. So this is how it is. This laser is shined on the crystal. Then you have a two signal and idler beams, and you send signal in this and idler in this. Then it is collimated and taking the coincidences. Then when you place a sample here, one signal photon is coming with respect to the other is starting the experiment. This one is you are scanning the sample so that you are able to image. So you see this UMBC, that how it is imaged using the single photons with very high precision. Please really understand. Such high precision one can image. So that quantum imaging has some powerful application. And importantly, if you do the classical imaging, right, so you can never go down to the sub short noise imaging. But whereas if you use a quantum correlations like what I discussed in the previous thing, that you can even push, okay, less than the short noise limited using the correlated photons. So this is the pi. So this is the examples it has shown. This is the setup they have used. The object which you want to image is the pi here, which was kept. So when this laser was sent through the crystal, the two photons are generated. So one photon is going through the sample, another photon is freely going. So by correlating these two, you see how clearly one can image. Okay. Importantly, it is a sub short noise imaging, which is not possible classically. Okay, and also as I said, in the biological, this is the most powerful application of the quantum imaging, because what is happens is that you might be seeing in the just I want to highlight this application. It's very useful for present humans, that many people are dying due to the cancer, right? So the main problem with the present technology is that you are realizing the either first stage or second stage or the third stage of the cancer after much more damage has happened to the body. Okay, what I mean is, if you see the tumors on the skin, or it depends on the which type of the cancer happens, that unless it has become a big, you are not able to identify, because you don't have a technology to image at a one cell level. I'm talking about single cell level. Anything in our body starts with only one cell. If you are able to detect the damaged cell at one cell level, so you can diagnose very early stage. you can protect human life further damage. This is very, very important. So present technology do not have such good imaging that you are able to detect at only one cell regime. One cell is very, very small, please remember. So anything in the body starts with one cell. But what we realize is that one cell damages the other, like let's say another hundreds of cells, then we are realizing that there is a cancer. Okay, since we don't have the technology to image one cell, so we are crossing the stage 1 or stage 2 or stage 3 sometime, then you are not able to identify, right? But if this quantum sensing technology is going to come into effect into the market, then immediately when one cell formation happen, then you know immediately that there is some problem with that cell. Then you can stop the damage, then you can save lot of human lives. This is a very, very powerful application in medical section. Okay, so important point is that you must know how to image with a single photon, which is a quantum source of the single cell, not multiple cells. Okay, single cell imaging is not that easy. You're just fundamental constitute your imaging. Okay. Okay, this is very, very important, which is a lot of research is happening in this direction because it has a such powerful application. So the conclusion, what I want to tell you is that imaging is possible where the classical illumination fails because it has a single photon is a quantum nature. So the image at such low scales, it is possible where the classical light or the coherent light could not image. So this is the one of the advantage in the quantum imaging. Okay. And another one is another powerful application is called quantum lidar. Okay, so which is most of the time it is used a correlated light. Okay, which is such as a entangled photon or the squeezed photon pairs. Okay, so just to enhance the distance measurements in the photon star, because when you send a light through the space, right? Normally what happens is that there are a lot of losses in space. You don't know what are the what are the objects come across, right? So if you don't know what are the objects come across, it's very difficult to image the because you lose the light, because when you're sending the light should come back and hit your detector, right? Then only you will be able to image, right? Once you send a photon, if the photon doesn't come and hit your detector, you lost the information about it, right? This is what it's, you see clearly that it's a photon starvation. Okay, so the place you don't have enough photons to collect a signal and to say something that you get some information from the space. Okay, so this is very, very important. So in this regime, what happens is that the pulses per, when you are sending 100 pulses, but the signal is not coming even, let us say 50 pulses, then how do you reconstruct what you are seeing? Okay, so most important thing is that out of 100 events, okay, very, very rare events comes single photon detection events. Using those events, signal reconstruction is people are doing it. Okay, so you can reconstruct, you must reconstruct with that information from the very, very rare single photon events. Let us see how the design is been done. I hope you can see it. Governments have invested lot of money to kind of design the detectors very high sensitively, because you should get enough light so that you can make a image. Most importantly, that the image is not close to you. In the medical section or anything, the image which you image is very close to you. But here in this field, his image is somewhere in the space that you have to image. Okay, it is not that easy. Okay, if you just think that if you enough light is, it's one best example I would give you is that when you are entering into the dark room, Okay, how do you know that something is there in the room? Unless you switch on the light, you don't know, right? So then once you switch on the light with your eyes, you are able to image everywhere in the room. Then you know. So it is a similar, because the photons are going, but there is no coming out of the photon, so that you will have some information about any object you want to far away from the earth to the space. This is very important application. Okay. Then the precision metrology. Okay. So precision metrology using the single photons, people are performing, and it has been demonstrated also. So aim is that to measure extremely small displacements, this delta x, and phases delta phi, and strains, if at all any strain is there in the samples. Okay, so the conventionally the people use interferometer displacement sensings. So in the interferometer, either it is a Michelson interferometer or the Mach-Zehnder interferometer. Okay, so it is a displacement. It is a basically the x is the is in if you change the arm length, so you are going to introduce a phase. Okay, this is how the typically how the interferometers looks like. In the case of LIGO Hanford Observatory, this is how it looks like, and also it is a LIGO L Observatory, Lucerne Observatory. So in this, people are trying to kind of use, okay. So the previously they used the classical light source, then they are having issues with the short noise, and they're not able to detect the quantum, they are not able to push the limits. Therefore, then they used the single photons and try to improve the aspects. And as I said, biomedical imaging, this is a powerful. So it will enable the non-invasive biomedical sensing at extremely low light level. Okay, as I said, since the light level is very low, you will minimize the photo damage of the cell while preserving the high sensitivity. Okay, whereas the classical light, you put a bunch of photons on one cell, you may get high sensitivity, but at the end you are killing that cell. This is very important. When it comes to the low light level, which is a single photon, okay, so you gently touch, not press, gently touch, but you are getting very high sensitive. This is very important. Okay, so then also you can do the fluorescence lifetime sensing, so which is which is useful for the local refractive index around the cell, and also pH, also most important in biology, and also oxygen concentration you can know, and also how the molecular binding is happening. And there are quantum optical coherence tomography, is that people uses the entangled photons to do that depth imaging. Okay, so it is like a you have a classical optical coherence tomography, but when you use a this is the classical way how you see, but if you use a quantum, it's a QT, so you will get that very high resolution images. So there is a clear difference between the classical and quantum. So you can even image, okay, you see the how the biological cells are being imaged with a lifetime in the nanosecond. You can see it with a lifetime. So that is only possible in the quantum. So therefore, this quantum OCT is a more powerful technique to do that in the case of biomedical engineering. Okay, so which means that the key message which you take home is that enables the single photon sensing, enables the non-invasive sensing at extremely low light level. This is a very important. Okay, so which is useful for the application. The last one, which is a fiber network quantum sensing. So this is a fiber network. As you know that everywhere you have a fibers, because you are getting the telephone signal through the fiber, and you are getting the internet through the fiber. You are everywhere in your life is full of with the fiber, right? One place to another place. So let us say usually called Alice and Bob. Everything you are sending through the fiber photons. Even if you want to send from one room to other room, the photon, The photon cannot pass through the walls, right? So you have to lay the fiber only. Okay. So while sending the fiber through, while sending the single photons through the fiber itself can act as a sensor. But it is not a single point sensor. It is like a distributed sensor because it is light will propagate through its way. Okay. It is like a continuously sense at every location. This is very, very important. And also it makes the link. Okay. Suppose one place to another place, the communication is easier in terms of quantum. While it is making the link, you will have a environmental changes. Okay. So if you have environmental changes, it can automatically detect that environmental changes very precisely. Okay. By measuring the coincidence counts or the correlations or any phase noise instead of directly detecting the intensity. Okay. So main important thing is that as you know that when you send a quantum light from the one photon from this place to this place, so nobody can copy that one in between. Alice can send a information in the quantum state, then Bob can detect automatically the state, but in between if somebody wants to tap that information, it is not possible through the fiber. Okay, so because nowadays it is possible because now all the technologies in a classical, but once you work with a quantum, so it is not possible. Okay, this is very important. So these are the emerging areas which I just brought. So I don't want to emphasize too much on it. Just I want to give an idea that how future is going to evolve. Okay, you are going to have a hybrid quantum networks. So as of now, we are in the quantum network status. This is what it's called quantum network actually. This is already quantum network. So you are going to have a hybrid quantum network, which is an entangle between the two single photons again. Then also you are going to have a quantum radar. Just imagine, now you have already radar, but you are going to have a quantum radar. That means that you are going to precisely locate the all the locations in GPS signal, okay? And it's precisely you are going to kind of do the all works in future, okay? And you are going to have a chip sensor. Now people are trying to do everything on the chip itself. So that can be, it's called as a quantum chip sensors. So everything is happening in miniaturization of the component. Now sensor, if it is this much size, in future it's going to be 1/10 of it or maybe 1/100th of it. So which is useful for the society. So then the single photon plasmonic sensor also it is coming up. It is still it is in the research stage, and also recently it is a AI assisted single photon detection has happened. This is also now AI and quantum as mixing together and to make a take advantage of both the sides. These are the emerging research directions it is coming, but okay, you asked me, sir, is there any challenges in these experiments? There are a lot of challenges. It is not that easy as what I described on the slide. When you do the real experiment, you will know how tough it is. Okay, so because I spend or our group and spend, other people spend a lot of time so implementing these things. Most important thing is source brightness. Okay, and versus purity of the single photon. So the main, as I'm saying that you you are going to have a low light level. Okay, okay. You give 100 photon, the system will give only 1 photon. This is very important. No matter how many photons you give, always you will have a 1 photon. Suppose you want to, because the brightness is what the brightness is. Suppose you want to make more brightness, you want to see the more single photons. Okay, in that process, if you give too much of input, you are going to lose the purity of the single photon. Instead of single photon, you are going to have a multi photon. Okay, which is very different from the single photon. Okay, so if you excite the single photon source with a low light, you are going to get a single photon source. But if you are exciting the single photon source with a high strong intensity, then there is a probability that you generate multi-photon. That means that in one pulse you are going to have two photons. So that means that you are not doing any single photon sensing experiment. Please remember that. So that means that there is a trade-off between the source brightness and also purity of the single photon. You cannot excite as much as you want because you want to increase the brightness. It doesn't mean that you can excite strongly the single photon source. That is there is a trade-off between the up to some extent only you can go. If you reach that intensity level in excitation, so simply single photon become multi-photon. So which is of no use for whatever the applications have been described. And important is the detector cost. As I said, we have a SN SPDs, right? Really good detectors. So the detector cost is very expensive, and it has to be operated at the cryogenic. So you need to go to the 2 Kelvin, which is a very tough job. Okay, then only you will get the state-of-art photon detectors. Okay, so if you, if anything you work at cryogenic temperature, then you want to use it for applications, right? That there is a problem, right? So because your working temperature is a cryogenic, but normal applications happens at room temperature. Again, there is a mismatch. So if you really want to solve the real world problem, so that means that you need to develop a detectors at room temperature, so that you you will be taking that one for the applications at room temperature. So you cannot keep detectors at 2K and use it for application, because we don't live in at 2K. So normally we live in room temperature, right? So therefore there is a need or urgency that if you can detect single photons at the room temperature with a good state-of-art sensitivity, it is good for the application. That is a very challenging part to develop that. And this is another thing, that you send a photon from, that is what is called, we call transmission loss or the fiber loss. You send a photon from here to this. So always when it propagates in the fibers, there is a loss. So suppose you have 100 photons here, then if you propagate like 100 kilometer, then this 100 comes down to 50. So the 50 photons are lost during the journey. Okay, just I'm giving one number. It's not necessary that always it happens is 50. Just I'm telling you physically. Okay, that loss has to be kind of killed. That means that you have to develop a fibers which do not have much loss while the single photon is being propagated. Okay, so once that loss has increased, right, the detection of the single photon at the end will be low. That's what it says. Okay, so because you lose the photons before it reaches to the detector. Then the other one is a integration complexity. So you need to integrate the sources, and you need to integrate the channels, which is the quantum channels. You need to integrate the filters, detectors in one platform. Okay, so it is like source is working room temperature, detector is working cryogenic temperature, and channel is working in different temperature. How do you integrate them in one platform? Okay, so when you integrate in one platform, so then it is this is a fantastic. So therefore, if you can develop the platform which can give you all three and at a same temperature, that would serve the purpose. This is a very important point. And the scalability. Okay, suppose you prepare a single photon sensor, and if you go and prepare the same, you will never get the same. This is one of the problem. Getting identical one is very difficult in these experiments. Okay, whether it is a emitter, single photon emitter, or whether it is a quantum channel, or it is a detector. Okay, there are a lot of things are involved. So when you are trying to scale it down to the small miniaturizing, then you are going to have a price escalation. So you have to target the detector. You have to target the detector cost such a way that anybody can afford. Okay, so in the future, that's very important. Okay, that is what all about. Then what is our contribution is, this is our group, which I think I showed you last 2 times. I don't want to get into it. These are the funding, these are the facilities what we have. And I just want to tell you that we are also working at, as I gave you, that single photon manipulation we are doing. This also I have already discussed, but I don't want to spend much time. And here what we developed is that, so this is the how the single photon is being formed. So you see that you have a tip and it is dipped into the quantum dot solution and it is removed, and only one quantum dot is being attached at the tip. Okay, so basically we are developing a single photon sensor, okay, which this tip can use. So other systems have some scalability issues. This, once this tip is confirmed that it is a single photon, so you have a single photon and you have a quantum channel which comes out of the system, then this is being detected at the single photon detectors. So this is how the photon correlation, which I am not going to discuss about it because I already described. So I hope you understand. These are the single photon counters which I am saying in our lab. Okay, these are the signal comes from the tip which is sitting somewhere here for the experiment. Then the single photons are falls on the beam splitter and it splits two sides, and one is detected by the APD1, another one is detected by the APD2. Okay, and it is being correlated. So first we see this in the photon counter. Then you see that very single step behavior. Therefore, that is a single photon, and you have a spectrum is very narrow. Then you see that you have at zero delay, you have a dip in the photon correlation, which means that the single photon detected at the tip of the fiber. Okay, so you are able to generate a single photon using a quantum dot, and you are able to detect a single photon using a APD. So you are able to manipulate the single photon using the fiber. So all three of them are integrated in a one platform. And importantly, I want to tell you that this is all the experiments are done at room temperature. Okay, which will have a lot of application in future. And I will conclude with this. Thank you very much. I would take the questions, please. Hello?
Yes, there is one question from Dr. Bhagwan. Sir, kindly explain how this single photon is not moving.
Single photon is not moving. No, it
I
is
think he's
moving.
talking about the experiment.
Moving. Single photon is moving. It is propagating. Okay, this is the tip, and a single photon is coupled here, and through the tip, single photon is detected at the end of the tip. That is feed it to the detectors. That the size, the length is approximately few centimeter, approximately few tens of centimeters. If single photon doesn't move, then it is very difficult to detect the single photon. It is moving through the fiber, inside the fiber. Is that clear?
I hope that is clear to Dr. V.S.
Yes.
Bhagwan.
Okay.
Is
Anybody
there
else?
any question from the participant?
Please. I hope you understand, or I don't know. Please understand that these experiments are extremely tough. That is very important.
Yes, sir.
Not that easy, because we are measuring the only one photon. E equal to nh nu. Generally, people work with n is being 10 raised to the power 6 or 10 raised to the power 5.
Yes,
Now
sir.
we are working n is equal to 1. Yeah, you should have a questions.
I think the question will come after the participants will see your YouTube lecture again. Then
Okay. So,
we will
Hi,
pass.
hey.
how are you?
I'm good. How are you?
Fine, fine, thank you.
Yeah, now single photon sensing is finished, then entangled photon now.
Yes, 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 yes,
Yes,
yes,
please go ahead.
yes. So,
I think I am done, right? Or any questions? If you have, please ask the participants to write to me. Then I can answer.
So there is no more question, sir.
Okay, thank you so
Thank
much.
you, Professor, for the theoretical and the experimental explanation of your things that you have done already in your lab.
Right,
So over to you, Avasthi, sir.
right.
Okay.
Now I can leave, right? My part is done.
Yes, sir. Thank you very much, sir, Professor.
Thank you. Thank you.
Our next speaker is already here.
Right.
Thank you very much.
Thank you. See you, Rajendra.
so bye bye.
Bye.
So thank you, Professor Jha. And again, welcome you to this session. Over to you, sir.
So, I can share my slides, right?
Yes, sure, sir.
Can you see my slides?
Not now. Now I can see clear.
Okay. Mm, It's got stuck. Can you hear me?
Yes, yes,
Yes,
yes.
sir.
The
Please.
title slide is clear.
Okay. Okay. I hope I will
Yes, it
able
is.
to. Yeah, it's
Animation is
fine.
clearly visible, sir.
Okay. Okay. Slides not moving though. Mm,
Yes, sir.
Let me cross check again. I say stop sharing. You may not be able to see the slide now, right?
Yes, sir.
This problem.
Maybe you can share the whole screen and open your presentation. Then it will move.
So you are saying that I share the whole screen, entire screen. Can you see my slide now?
Yes, sir. Your slides. Yes, sir.
Okay. As soon as I'm trying to go for the pointer, it's getting stuck.
Okay.
So it's showing pointer now. Hopefully it should move. It's moving. Fine.
Yes, sir. It's moving.
Yeah,
It's
fine, fine, fine. So good afternoon, everyone, and I would like to thank the organizers for giving this opportunity. The titles of today's talk, as you can see, that it is entanglement-based sensing application. Now, I have, since I earlier gave a few lectures, so you know me, I'm Rajan Jha, coming from IIT Bhubaneswar. And whatever the view graph, what you are seeing in these two diagrams, they are largely telling you some signature associated with entanglement. So as we move ahead with the slides, this will be clear. So what I will be talking about is, will quickly give you, some slide about, some numbers I have discussed earlier also about classical and quantum sensors. And then I will try to tell you more about the whole focus will be on quantum entanglement and how it can be generated, detected, and how its application can be utilized for sensing. So this is an older slide, and I believe if you can recall, when we talk about sensors or sensing, then you have two type, the classical one and the quantum one. Now the classical one is simply, as you can see here, that we are talking about classical objects like day-to-day cricket ball, for example. The size of these particles are much bigger than the particle which shows the quantum behavior. Especially the quantum behavior are shown by particles which are of subatomic in nature, and it should be comparable to the de Broglie wavelength. It show that it exhibit a strong quantum confinement, so that it can show you some of the features like the quantization of the energy, or energy will rather than being a continuous energy level, it will have some steps in the formation of the energy level. So classical systems, all of us use in our day-to-day life, all type of different type of sensors, starting from electrical to chemical to thermal and acoustics. In quantum, different sensors like atomic clock are there, quantum gyroscope are there, quantum thermometer. Now these can be based, all these whatever I'm showing you can be based on a concept what is called as a quantum entanglement. And the major topic for today's talk is related to quantum entanglement. So let's try to focus more on this. And if you see, it is not a very, this word entanglement is not a, it's not a very, I should say, something new, but the great Einstein, he gave this way back. He gave this way back in the last century, where he said that quantum entanglement is a spooky effect as a distance. So his idea was that two particles which are entangled, irrespective of whatever the space is between them, what irrespective of the fact that how far they are separated, are directly correlated. So entanglement is more or less like, you can say, twins. So correlated means if you try to perturb one, the other will get perturbed. But one of the very important concepts what quantum mechanics is that if you want to measure, if you want to measure some particular state, then it will collapse. So the quantum mechanics never allows you to predict the state of a particle without, it destroyed the state which it wants to measure. And this is also called as a non-cloning theorem. And in case of an entangled pair, if you try to, measure one measurement of one collapse, if you were trying to measure one of the state, then the other collapse. Now this is you can just think that if you try to catch something, it will disappear and it will appear at another place. So this is what you can think it like, what entanglement is all about. So generally photons, we will be talking more about photon point of view. So generally photons, if you want to, have photons which are, so now the point is photons exhibit certain properties. All of us know that. Photon can be characterized by certain features, and one of the features, strong features of photon is let's say intensity, or you can say that strong features is polarization. Now in most of the entanglement experiment that what we do, many times we discuss about the polarization which are entangled. So now what do you mean by polarization and entanglement? It means something like that. So that if you have two photon and they are entangled in polarization, again I repeat, entanglement in polarization means that if you want to measure one, it will collapse and it will appear in the other, the state will preserve and it will appear in the other state. That means if H represent the horizontal polarization and V represent the vertical polarization, and if these are the linear superposition of two, you know that from the basic quantum mechanics, we know that it will be 1 by under root 2, the combination of linear as well as vertical polarization. Now, if they, let's say if you have two photon, you can see here that this is a vertical polarization state, what it has gone. You see that it moves to one of the detector, and if you have another polarization state, then it can be, it can go to any one of those detector. So you have to see that to which particular detector it goes. So you have to measure one of these states, so as soon as you measure it collapse, but it then appear in the other state. So the polarization associated with the photon can be either vertical or it can be longitudinal. One of the most important, I should say, one of the most important way in which entangled photon pairs are generated, and this is also commercially available, is generation of entangled photon pair source using a non-linear process, which is called as a SPDC. Now, SPDC is a spontaneous parametric down conversion. This is a non-linear process. Unlike uh, a linear process where polarization is directly proportional to electric field. But in SPDC process, which is a non-linear process, polarization is not proportional to electric field. So how we define polarization? Polarization is basically dipole moment per unit volume. That means if you take a dielectric material and try to incident a field on it, you know that the dielectric will get polarized. But if the oscillation of these dipole, which is formed due to the incident electric field, if the oscillation of these dipole is at the same frequency as that of the incident frequency, these are linear material. But if the oscillations of this dipole are, if the oscillation of these dipole are not harmonic or it is anharmonic, then it started producing other frequencies. Those frequencies are maybe, higher frequency, or it can also produce lower frequency. And this is what the nonlinear process consists of. You have some laser source, and then this is what is nonlinear crystal, as I was talking to you about, that it is some nonlinear material. It is some sort of a glass or some sort of a dielectric, where if you incident a laser light, then the dipole that will get formed here will not oscillate in a harmonic fashion. It will oscillate in an anharmonic fashion. Now, anharmonic fashion leads to the generation, anharmonic oscillations lead to the generation of some of the photons which are different than the incident photon. So these they are crystals which are called as a nonlinear crystals, which follow Chi2 process. Will not go into these detail, but then it follows, it gives you have one pump and it gives you signal as well as idler. Needless to mention that they do observe, or they do possess the momentum and energy conservation. So the omega pump has to be equal to omega signal plus omega idler, and the k vector for the pump has to be equal to k vector of the signal and idler. So both these has to be ensured, and this is how you are able to produce two beam, or I should say, now these two can have two different polarization, as I discussed earlier, and they can be entangled. So here the entanglement can be in terms of I should say polarization, or it can also be in terms of intensity. So these SPDC process basically are of two type. Now, what are the two type of SPDC process? You see, polarization of signal and idler photon. The two photon that comes out, the polarization of these two. There are two type 1 and type 2 SDPC process. That in type 1 SDPC process, it has the same polarization. That is both ordinary, which is called as a O, or extraordinary. So it has same polarization. Both going to have the same polarization. But in case of a type 2 type of SPDC process, the polarization is orthogonal. That means one will have ordinary polarization, or another will have extraordinary polarization, or you can say that one can have a vertically up polarization, another can have a horizontal polarization. Now, another interesting aspect of SPDC process is the emission pattern. So if you see the emission pattern, if you get a single cone, then you are in type 1. But if there are two cones which are intersecting, as you can see that by recording through a camera, you can see that, then you say that you are in type 2. The spatial separations is very hard to separate here. Therefore, you see only one cone, but these are easily separated by what is called as a polarization beam splitter. So if you use a polarizing beam splitter, you can separate out the two cone. And this is what exactly SPDC type 2 process has the advantage. So you can see that it has having one cone, these are having two cone, but you can separate these two cone using polarization beam splitter. So polarization beam splitter works as a that if you incident polarization, two different polarization, it will separate the horizontal and vertical polarization. Now, as far as entanglement generation is concerned, entanglement here requires two crystal and the interferometric setup. I will be discussing about this interferometric setup, but here it requires two crystals. Entanglement itself required two crystal, but here it naturally produces polarization entangled photon. That means here you get a polarization. Since these two cones are there, so you basically get a entangled photon. But in order to create, as it is obvious that because here you get only one cone, so you require two crystal, and then you try to entangle the photon coming out from both the crystal. Now these are the typical materials that I used. These are non-linear crystal. What has been shown here, one is beta barium borate. This is a widely used crystal for type 1 or KDP, and this PPKT or periodically poled. KTP also people use. KTP also people use lithium niobate crystal for such type of application. So this slide takes you to how you basically periodically poled lithium niobate, or how periodically poled crystals can be utilized for creation of let's say two type of beam like idler and signal. So in case of a periodically poled crystal, you basically flip. You see that you flip the direction of the field is flipped here. So basically these domains, it get flipped in opposite direction, and this is how this is periodic in nature, and these are two separated by some lambda, as you can say. And depending upon whether you have the k vector of the signal and k vector of the idler in the same direction, so you get effective k, or you can have it is in opposite direction. So accordingly, it is either called as a co-propagating phase matching condition, or it is or otherwise it is called as a counter propagating phase matching condition, depending upon you have omega pump, and you get in the same direction, you get omega s and omega I. But here you see omega p, and omega is in this direction and omega s is in other direction. Therefore, these are counter propagating phase matching condition, and this is one of very standard technique for the generation of entangled photon. The same thing has been shown here by showing that if you take some glass, and then if you coat ITO on that, and then if you make some AU film, so this is also one way in which people have created. So these are some of the plasmonic type of structures where people have tried to created the two polarization. They have tried to separate the two polarization. Further, nowadays, a lot of research work is getting people are trying to do a lot of research work on meta surface based entangled photon, where you try to create some sort of a meta surface, especially using lithium niobate, and then try to see that can you create two entangled photon by incident with some frequency. Can these two omega s and omega can these be entangled? And there are a lot of research work which are going in these directions, saying that the two photon that are either created by a periodically poled system, or by making some sort of a patterned gold particle or silver particle on some glass coated ITO, or by making some meta surface. This is another way in which people have been making these entangled photon source. Another way in which entangled photon source can be created is by using a quantum dot. So what you do here, you have some quantum dot, you excite these quantum dots, and then you allow to pass through some switch. You measure them. You measure them on both sides through some type of APDs, and these you correlate these two APDs. We'll discuss about that, and then when you correlate them, you can identify that whether these two are correlated or not. These are some of the very latest research where people have reported about using semiconductor wire or nanowire, where they are trying to see that it started with some dipole, and then you are trying to see that these two are correlated. So you measure one in towards one side, and it will going to get put on the other side. Then this is a very another interesting area which is called as a superconducting quantum dots. People are trying to have latest technology which are built using these superconducting quantum dots, where you can have both vertical polarization and horizontal polarization. And if you try to measure them, the one collapse and you can measure the other. People have also used some circular Bragg rating based structure and then try to excite it, and then it can be seen that these two are coupled. This is a very recent paper from Nature Physics 2024, where they have shown that using some sort of a structure, or using some sort of a waveguide, and if you put quantum dots in between, guide them suitably, then these are entangled, polarization entangled, and as it propagate over the waveguide, you can make them entangled in energy and time. So these are some of the ways in which people have I have tried to demonstrate some of the ways in which people have basically generated these entangled photon pair. But generation is one thing. So either you used SPDC process, or you use periodically poled systems, or you use pattern gold, or you use uh, other systems where meta surface can be utilized for the generation of entangled photon. Once you have created, then you should also know that whether the photon that has been created are entangled or not. So people, what they do is they do this HOM interference, or Hongo-Mandel interference. He also got the Nobel Award for uh, this Mandel process. Mandel got the Nobel Award. So here, what you do, you take two photon interference, and this is what in one of the last slide it was shown, that you have some pump pulse here. Of course, it goes through a Chi2 process. It generates the two photon. You try to put both them on beam splitter. You move them in time about either this direction or this direction. You know that if the distance that can be separated is c times some delta. Delta is the shift that can be measured, and then you try to correlate on these two detector. So using that, you can identify these type of molecules what are existing in one of the arm. So this is a very standard technique which are utilized for sensing application, and a lot of research people have been doing in this direction. I will be discussing about some of them. There is another interesting aspect that how the photon can travel. It is called path entangled, or traveling path possibility of photon traveling path. That if you have some sort of a region on which the photon is incident, then photon can be either on this two side or it can be on opposite side. But you see the opposite side photons are off. You can imagine them to be different path. So these are two, either it can be on the same path, it can be on opposite path. So this is basically for routing the photon in different direction. It can be routed in different direction. This is used for routing. So when you do this coincidence measurement, you get some D1, D2 coincidence measurement. You'll see that there is some very strong dip signature, which is the measure of which is a measure of entangled photon. Now, one of a very important aspect of entangled photon is the photon should be maximally entangled, and for that, the famous Bell states have been defined. So Bell states are the four maximally entangled qubit state. So if you have, these are the four state, phi plus, phi minus, psi plus, psi minus, pi plus, phi minus. You see, these are 0, 0, and 1, 1. It is a combination of 0, 0, and 1, 1. What does this the first equation means? That there is a 50% of chance of measuring 0, 0 state, or when you say and 0, 0 state, you can also put it in vertical or horizontal. So from this equation, we mean that there is a 50% chance of measuring the 0, 0 state, and 50% of chance measuring the 1, 1 state. But in this equation, you will never going to get 0, 1 or 1, 0. That is for the another psi plus state, where you get 0, 1 and 1, 0. But once you have this 0, 0 and 1, 1, that means either you measure this or you measure this, then these are supposed to be called as perfectly correlated systems. So if the first qubit is 0 and also the second is 0, and if the first is 1, the second is also 1. So if that is the case, then the system is called as a perfectly correlated systems, or for perfectly entangled systems. The Bell state has there are a lot of important advantages associated with the Bell state. These are some of the advantages what I have placed to you here. That Bell states, these are basically, as I told you, maximally entangled states of 2 qubits. They represent the strongest possible quantum correlation between the two particles. So every time once you want to do the correlation, you want to identify the quantum correlation, and this correlation is a way related to entanglement, then measuring the Bell state, you can say that whether the correlation is strong or not. This also proves that the quantum entanglement is non-classical, and therefore it is quantum. This is not non-classical, and this form the basis, a strong foundation for the future communication protocol. And all of you, I will say that you must be aware that a couple of years back there was a communication link that was shared between China and Austria over satellite communication, where these were measured, these Bell states were measured by them. And I think that distance, I don't remember, but I think it was few thousands kilometers between Austria and China that this Bell state protocol was established. And the entanglement was also studied at 2 different locations, separated quite far apart. So now these are systems which are already in place, and in some part of the world, these are also being utilized for quantum communication within the country. So and all these, whatever the experiment that you have been hearing in the news, or that for that matter, the experiment that are going around are the one which uses this concept of uses the concept of entanglement, and they measure the Bell state in order to prove that whether the photon that is being generated are maximally entangled or not. So this is some further I should say that for some further insight. This is what I showed. I mean, this diagram, if you see that if you have subphoton, entangled photon goes here, then entangled photon from here, and then you have this. So this is about how the experiment was done. Of course, these are a small distance, whatever has been mentioned here, but in principle, this has been established over thousands of kilometers. Now the 00 or 10, whatever we have said. So how the entanglement photon are detected? That means you produce polarization entangled photon in Bell state. So you know that this psi minus means that this is one of a state out of the 4 state. So you have combination of horizontal and vertical and horizontal polarization. Now you choose one of the bases. These bases are something what will be shared for Alice and for Bob. So you choose one of the bases, A to be 0 and A prime to be 90, and similarly B to be this. And these are some bases that to be chosen, which will be shared between 2 people separated far apart. And then you try to measure the coincidence. You measure the joint detection probability of horizontal, vertical, vertical, horizontal, and vertical for each setting. For each setting, you try to measure them. You see that this is how it has been shown here, that you try to measure them using the coincidence detector at different place, and then you try to calculate the correlation function. Now this is a correlation function. You can look into the literature for more details about that. And if you test the Bell inequality, it has already been demonstrated experimentally that this S, the Bell parameter, whatever you calculate in this way, it is greater than 2, then you say that the photon are entangled and Bell inequality is violated. Generally, the Bell inequality for quantum mechanics prediction shows that S will be less than 2 under root 2, but S more than 2, greater than 2 shows that the photon are entangled. These are mathematically proven, and also this has been experimentally achieved. Whenever the experiment has been conducted, people have experimentally achieved these numbers in the lab. Okay, so now there are few commercially available entangled photon detectors, and these are the detectors which we also use in our lab now. Largely, our lab works with avalanche photodiode. These are the avalanche photodiode detector. They are very, very sensitive detectors. Then another very sensitive detectors are superconducting nanowire single photon detectors. These are quite costly detectors, and using them. These are costly, and therefore using them require you need to have a lot of expertise also to use them. Unfortunately, in our country, we are planning now. There are groups which are planning to make APDs and SNSPDs for future applications. And then there are transistor edge sensors, which we don't use. Some of our collaborators use SNSPD. In our lab, we use APDs. The APDs that we use in our lab are both fiber coupled, and also these are open optics for open optics application. So these are some of the important aspect of all these three detectors, and you must know, because if you have to do experiment or research in this area, then it is important to know that what are the key operating points for these detectors. So these are avalanches. Basically, it is a some sort of a multiplication of electrons within the semiconductor. Here in superconducting nanowire, photons break superconductivity in nanowire, and then you measure them, and then is transition is sensor photon heat superconducting film. So it is breaking, it is heating, and this is some sort of a multiplication of the electrons in semiconductor. Please note why we use avalanche photodiode, because we are interested for single photon generation at room temperature. Many of the experiment where people have been doing quantum computation or quantum communications at cryogenic temperature, they have to go with such SNSPDs, that is superconducting nanowire single photon detectors. The reason being that these detectors cannot work at room temperature, and you know that even still at room temperature you don't have a superconductor, and therefore you have to operate all these at cryogenic temperature. Same goes for transition is sensors. Please note that these are also more sensitive than APDs, depending upon what you want to monitor, but they are sensitive, and therefore operating them is always going to be a challenge. And this is a challenge which is being faced by people who are working in this area, that they have to do all the measurement at very low temperature. Needless to mention that whenever there is a challenge, there is more opportunity, and this is where what you see, that the detection efficiency of superconducting is close to 98%. But majority, whatever you do in TES, transition edge sensor, you always have a possibility of detection efficiency of more than 95%. So challenges here are more, because you see the type of temperature you are talking about here. Here it was Kelvin, here you have millikelvin. Now, using such ultra cryogenic type of systems is not easy. Development is not easy. Maintenance is very, very tricky. And performing experiment at these numbers is never easy at all. Then, of course, one of a very important aspect for any type of detectors is how much is the dark current count rate. And you see, as you go ahead, better the systems like photon breaking the superconducting film, you see these dark currents count rate are very low. You basically require a systems having a very low dark current rate, and TES basically qualifies for that. Unlike avalanche photodiode or SNSPDs, which have relatively higher dark current count rate. Please note, this is a very important aspect. Nowadays, most of the experiments that are being done in the area of quantum optics, they are largely confined to visible or to some extent in near IR. Anything, possibly you will see hardly there is any paper working beyond 1550 nanometer. And one of the very obvious reasons is you can see that there are no detectors available in the market. There are no detectors which can go beyond near IR, that is in mid IR and far IR. Detectors are not possible currently in the market, and therefore any experiment if you want to do, especially all of you know that, especially water has a very strong signature in around 2 micron. So any experiment, biological experiment which you want to do using, let's say, where water is significantly present, and you want to use a quantum measurement or quantum sensing application, which such type of systems for, let's say, bio applications, you will struggle to do that experiment, because you do not have a detector going beyond. Of course, you can always say that avalanche photodiode is having around 1700 nanometer, but please note that as you go towards the higher side, this dark current rate, count rate increases. This is number you reach here, and as far as efficiency goes, it comes around 50%. So efficiencies come down, dark current count rate goes up. So anything more than 1550 is a headache to be detected. And this is one of the prime reason that why people are still struggling to go beyond 1550. Now, this is another important aspect. What does these says that count rate capability up to megahertz? This is megahertz. This is low like kilohertz. These are people are trying to push it to kilohertz to megahertz also. What these count capability rate are basically is that how if you have a entangled photon source generated, then how fast you can measure them, how fast. So just for example, when you use internet at a home, you always see that what is a download speed like kbps or mbps. So this megahertz speed, whatever we are talking about, is the speed at which you'll able to count those single photon, entangled single photon that is being generated. So these are very, very important. But you see here, you have very good numbers like in terms of detection efficiency, but then the count rate is coming down. And these is extremely difficult system to handle. Needless to mention that the price is highest among all the three. So with TES based systems, you are more than 2 crore. With SNSPDs, this is close to around 1.5. And what we use in our lab is around these, because you require quite a bit of number of that in order to do experiment. You require 4 or 5 of such APDs in the lab for measurement. So the whole idea is, as I earlier also mentioned in the one of my last lecture, that the major challenge that quantum optics community is facing is the high cost and a big risk associated with the measurement. So these are numbers which are for which you have to put a lot of money. Okay, so then we come to the some of the imaging part or some of the applications of quantum entangled photon, this sensing and imaging. So one of imaging using application of entangled photon is called as a ghost imaging. The word itself shows as a ghost, that means something which is you can't see and then still you can image. So this is again a standard nonlinear crystal. You know that you're going to pump it from this side with some suitable laser source, and then you have signal and idler that is being created. But you see, this is with some shape of 8. These are entangled. That means they have the similar features. So if you have some object here getting illuminated by the signal, and you have some using the idler, you have some scanning detector or camera in the idler plane. And then there are something what is called as a single pixel detectors. These are also called as a bucket detector. You try to, using the single pixel detector, you try to correlate these two, because although there is nothing here, you try to correlate and then record on CCD device. So if you see the classical image, if you see, then there will be nothing. As idler photon do not encounter any object, there is no object in this idler photon, and therefore whatever you are seeing classically, this is not possible. But in quantum image, if you see the near field image, you will get an upright position due to the position correlation. So this is again entangled system. So you do the position correlation. The correlation measurement that you do, it can be done for different part, and in this particular case, it is being done for the position part. Similarly, if you see in the far field, it get inverted, and this inverted due to the momentum anti-correlation. Now, these are some of the terms which are widely utilized by the people who works with the ghost imaging based systems in their lab. These are some of the advantages of ghost imaging based systems. Although these systems look quite simple, but using them in the lab is not that easy, and one has to be very, very careful in maintaining the one has to be very careful that the power that you get with the signal, or the power of the laser light that you get with the idler, which are correlated, these has to be stable. This cannot be that these are unstable power varying with time, and therefore the crystal has to be robust. So all these parameter influence the imaging quality or imaging pattern. So the advantage of ghost imaging, it reconstruct the image of an object using correlation. So as I told you that here you do the correlation with the the correlation can be done with the position correlation, what you are able to with the position, and then you try to correlate the two photon of the different arms of these two different arms. Here, no direct imaging as such is required. Otherwise, you could have to also put something here in this area. This is another important aspect, that these ghost imaging can even work with a very low light. It can, even with a very feeble light, you can create them. The advantage only is that here the advantage is that even if you have a very dim light, you can still do the imaging. But for, as you know, that for imaging you require some very strong light to illuminate the object so that you can image. There is there if the media is having some sort of a scattering or noisy, then it become slightly difficult, and one has to find a way out to suppress those noises. These can be very useful for remote sensing, like if you want to monitor, if you want to image some hazardous zone in somewhere in harsh environment or in a space object, or for even that for matter cells and tissue. Now a lot of research is going on this bioimaging using this, and also people are now trying to see that can these quantum imaging or ghost imaging be utilized in turbulent and fog or a smoke media. There are a lot of research going in this direction in the country also. Okay, so another application of you have heard about optical coherence tomography. Now people have utilized or extended this concept called as a QOCT, or quantum optical coherence tomography. So optical coherence tomography is a old technique, and it allows you to do imaging. Uh, you know, uh, you do the imaging frame by frame, and then you stitch them to get the final image. But then now people are using this concept of entangled photon. Again, you see you have a biphoton which is there, and then if whatever the sample you have, you basically have one as a reference arm. It goes to the single photon detector. Then you have a sample arm, which is basically the ones which you are interested to scan. And then again, these come to the beam splitter. These are the two beam splitter. They basically get sort of interfered here, and then you see it carries some. This is a green arrow. This is a red arrow. But now in both these case, now since these are entangled, it has both green and red arrows in these two. Now you basically do the coincidence again. Though when you do the coincidence, it will come along with the features available with the sample. So this was a simple reference mirror. This is a sample. Only thing is the sample need to be reflecting in this particular case. Otherwise, you're not able to do the recording. You're not able to do the recording. And then you do the coincidence measurement. And this is what people have shown for the Sigler and Idler. For these are for two different one case of a healthy person, another is for a case where person is having a loss of memory. Again, the advantage of quantum OCT is that there's a the dispersion cancellation is there. Even higher order dispersion can be cancelled, which therefore have a better, allows you to do better axial resolution. You can have a high axial resolution because the dispersion get cancelled. Then you have sub-short noise sensitivity. Even for very uh, noisy signal, it has a capability to reduce the noise beyond the classical limit, and then that can be utilized. To do the imaging. As all these quantum systems have the advantage of using a low light operations, so these can also be very, very useful to illuminate system, because all of us know that biological systems are very sensitive. Biological cells and systems are very sensitive to intensity of the light, and therefore there is a strong feeling among the quantum imaging community that if you do the imaging using these correlations method, where very feeble photons are intensity of photon is very low, and still it does the imaging. So it can be very, very useful for bioimaging application. And this is what a lot of research work is going in this direction. Now, but all these features basically gives you a very strong coincidence counting, because it suppresses all the background noise. When you do the correlation, you have to ensure that the background noise get suppressed, and any noise that comes because of scattering media. Please note that whenever you have a biological sample, the biological sample in itself is a very strong scatterer of the light. So using this quantum enhanced, or I should say quantum enhanced tomography, what you can do is, even for the media which is very, very scattering or scattering media, still imaging is possible, since the light that you have, what you have is low, and scattering is high, but still you can suppress some of those background noise, and you can have a very good signal to noise ratio even working with the scattering media. Then there is, this is important, another very important aspect where people have been using, this entangled photon for spectroscopic application and for molecular sensing applications. Now, all of us know that Raman has a very strong, for molecular sensing, Raman effect has been utilized in past. This is also very recent literature where it has been shown, has been shown that, you can do using the entangled pair, you can able to identify, you see, they are able to identify, these are the correlation parameter on the screen, whatever you are seeing. So you have some source, you have some nonlinear crystal, you create entangled photon, these are photon. Now these two will going to entangled photon will going to interact with, let's say, any molecule. Now these two molecule, because you know that these photon will going to excite them, they will come down, they will going to emit, and the emitted one is again entangled. Now emitted one is again entangled, and these entanglement, if you can measure them suitably, suitably, when I say measure, basically if you can correlate them suitably, you can get the specific informations about these molecules, what type of molecules, what type of bond they have, and stuff. And there are a lot of research that people have been doing that, from making how to make source and how to use them for sensors, different type of finding the different type of sensors, and then try to correlate them using the coincidence measurement. This is one such experiment. This is a very, very recent experiment. I just took it from some of the recent paper, just to tell you that what people are trying to do, what has been done in past for interferometry using homodyne and heterodyne based system. The same now people are trying to replicate with the quantum systems, and therefore you can have some, you see these are some sort of a classical COM, this is a local oscillator COM, and this is an entangled COM. Now, classical COM and entangled COM are coming from, again, nonlinear process. You see, they are different. You put them to beam splitter. Now, these are entangled signal COM. You have this entangled signal COM. Again, this is a local oscillator. That means you can say that you are going to have two beam one. Now, this entangled signal COM is passing through some gas cell. Now, this gas cell, whatever you are seeing here, this gas cell are the one where you have put those molecules of the gas cell which you are interested to study, and then if you put it through beam splitter, and then you again do the coincidence measurement. So you can do the coincidence measurement, and then you can, from the coincidence measurement, you can identify what is the nature of the gas that has been present. Now these, as I mentioned to you, that they will the signal will be less noisy, and also with very low light or with very low intense photon, you can do the measurement. Again, advantage of these spectroscopic sensing, it's cancel even higher order dispersion, and which gives you improve in axial resolution. This also enables noise reduction beyond classical limit, because this is where the advantage of quantum comes into play. The people many times ask wherever you have a discussion that what is the advantage. These systems were earlier also being used for the detections of let's say gaseous environment or detection of biomolecules. Why quantum is required? This is where you have the major advantage, that sub-short noise sensitivity is there, that it enables noise reduction beyond classical limit. It suppresses the noise and it gives you a very clear signal, and therefore these are having a lot of advantage. And another important is it's use a very low power of light that can be utilized for biosensing application. It suppresses the background noise and therefore it improves the signal to noise ratio in the scattering media. So you can work with a scattering media, you can work with low noise systems. It suppresses the noise. You can work with very low intensity. Therefore, these are advantageous to biological systems, so on and so forth. So if in all the three cases of the sensing, whatever I have discussed with you, you can see that all are having the common advantages. These shows the common advantages. This one diagram shows the temperature sensing using again entangled photon source for the two polarization, horizontal, vertical, horizontal. You can see them. You can see these signatures, and then you have horizontal, and vertical. These are the two loops what you can see, and then you can again do the correlation measurement, and you can then using the coincidence measure, you can identify what is a typically temperature, what was a temperature that has been utilized. So these are quite sensitive. You can see that the measurement has been done at a degree of 2 degree. Now again, these 2 degree can be done with a classical system, but what is the advantage of quantum? So same understanding that scattering temperature measurement in a scattering media can be done with accuracy. Low photon is required here, and it is less noisy. You basically suppress the short noise and stuff. Okay, so what are the advantages and limitations of entangled photon for sensing? You see, the measurement precision, it basically can surpass what is called as a standard quantum limit, SQL, but the limitation says it require a high fidelity entangled state. When you say a high fidelity entangled state, it's difficult to create a very bright photon. It's difficult to create a very bright photon because whatever the laser power that you use to pump, there is a lot of attenuation that goes in the system because there are multiple components that are utilized. So creating a high fidelity entangled photon is a big challenge. Then advantages is these are, it has a high phase sensitivity for interferometry application. But if you are not able to have sufficient, uh, photon is getting lost, then the sensitivity reduces because you utilize those photon for sensitivity, and therefore sensitivity degrade rapidly upon photon loss. Quantum correlations, if you see that non-classical correlation enable improved parameter estimation, but here the decoherence reduces quantum entanglement strength. So you have to always ensure that you have to beat the decoherence. Somehow or the other, the system should not should not have decoherence aspect associated with it, otherwise the entanglement will get reduced. These can be utilized for remote correlation measurement, but then there are require some transmission channels, stable transmission channels, which is difficult. Information coding is possible, but then preparation of such state is very, very difficult for coding. Ghost imaging and sub-diffraction techniques are there, but here, if you have a low photon flux, a lot of time is required to do that. Now, integration with fiber systems, these are compatible with the long wavelength, systems. But then, that fiber has a natural dispersion and losses, and therefore it can reduce the entanglement quality. So the idea whatever I am trying to emphasize here is that some of these things, whatever we are discussing here, has been some positives are there in terms of you are surpassing some SQL, you have high dimension entanglement, you can do imaging, ghost imaging, compatible with telecommunication wavelength, but then there are some challenges or limitations. These limitations in future research one has to overcome. So what I have tried to discuss in last around 55 minutes is that I try to tell you that what are entangled photon, what are the different ways in which entangled photon can be made, either it is by SPDC process or using some meta surface. You can create those entangled photon. or using some metamaterials, you can create those entangled photon, or using some other nonlinear process, you can create those entangled photon. Once you have created, then you can detect them using HOM interferometer, and then you do the coincidence measurement, and from coincidence measurement you try to see whether it is which state you are trying to measure. Apart from that, once you do the correlation or coincidence measurement, then you require some sort of type of a detector, and there are standard three detectors. One is APDs, one is SNSPDs, and another is TS. And we have discussed about the different limitations and advantages of these detector. Largely, we have seen that the price goes on rising from APDs to TS, and it of course offers advantages like in terms of dark current, low dark current rate, low dark current count. Efficiency for APDs is lower than SNSPDs and stuff, but then the price is also low. And the most important aspect is that APDs can work at room temperature, unlike NSSPDs and TS, which can only work with cryogenic and subcryogenic temperature. Then I try to discuss with you about ghost imaging, that using entangled photon source, you can do the ghost imaging. You can do temperature measurement. You can scan the different tomography. You can do the tomography layer by layer, and then you can stitch them. And in all these process, what we realize that you require a low photon. The signal is the signal to noise ratio is good. The system itself can be, since low photon still give you the coincidence measurement, therefore system can be utilized for biological applications where low photons are required. So with this, I will conclude that I try to give you something about classical, in the beginning, about some classical systems, then quantum systems we discussed, about entangled photon, then some sensing, where entanglement can be utilized for sensing purpose, and then the advantages and limitations of the entangled photon. So with this, I basically thanks the group. Some of these are postdocs now abroad. Some of them are still working in the lab. Some of them are doing PhD, and some collaborators. And you know that all these, you can't do experiments without money, and therefore I'm really thankful to National Quantum Mission, who has been very, very generous in giving the funding to do some of our quantum related work. So with that, thank you very much for your kind attention. I will be happy to take a few questions. Any questions?
Till now, there are no questions in the chat box. So participants, if you are having question, then write in the chat box.
So somebody is saying that any specific application experiment carried out in your lab. So we are in our lab we basically use quantum emitters based systems, and not the systems using uh, uh, SPDC process. So the experiment that we are doing in our lab is we are creating single photon using quantum emitters, not using the nonlinear crystals or nonlinear process. How effective the hardware in India is capable of doing quantum computing. I think a few groups in the country are doing research in the area of quantum computing, and there is some success rate is there. Some success rate is there. Can we simulate in our PC? Yes, you can do some of the simulation in your PC. You can do some of the simulation in your PC. any tool for simulation. You can use a finite element method, finite difference time domain for simulation, FE and FDTD.